Hey guys, welcome to Unit 2, Section 3, Velocity. So in this lesson, we're going to learn to use vectors to model and solve problems arising from real-world applications involving velocity. So there's some crossover here with physics class, but it's always good to see these problems in a couple different ways to help us understand. So let's look at velocity here. Well, velocity is a vector quantity. And it's just speed, but with a direction. Now, when you're driving a car, right, your speed and sometimes direction can be found looking at the speedometer or GPS. But other types of vehicles, okay, sometimes have external forces that change your speed and velocity and could cause your speedometer to lie. So can you think of what types of vehicles could be affected like this? And of course, what I mean is vehicles that are not grounded, right? So boats and planes, right? Because sometimes what happens is, in a plane, you could be flying, but the wind could be pushing you in some direction, right? There's an external force being applied to the velocity that you're intending. And so there are certain problems that arise out of this, like how do you figure out where you should point your boat or your plane in order to account for these forces? So today, this is what we're going to look at. So first, a bit of terminology. So the air speed of a plane or the water speed of a boat is the speed that would register on the speedometer of the vehicle, like a car. All right, so this is the speed that the vehicle is registering independent of any external forces like wind or current that are being applied. Right, so air speed or water speed. Whereas, in contrast, the ground speed or resultant velocity of a plane or a boat is the actual velocity of the vehicle with those registering factors. And really, there's only two types of problems that we end up looking at here for this section. And you're either trying to find the resultant. So where do we end up if we're heading this way and the wind or the current is pushing us? Right? Or where are we going? Right? So finding a resultant, or finding a different different vector given a desired resultant. So if we want to go to some place, how do we get there? What is how do we have to change our course? Or even can we get there? Sometimes is a version of this problem. So all of these problems that you'll see here and the ones in the homework can be divided into these two categories, which is a nice way of just helping us to understand what we're doing. So example 1 says a plane is heading due north with an airspeed of 400 kilometers an hour when it is blown off course by a wind of 100 kilometers an hour from the northeast. Part A, determine the new ground speed of the airplane after the wind strikes. So the idea here is that our ground speed, which is our resultant, right, velocity is going to be changing as soon as the wind hits because it's now pushing us somewhere. So let's use two diagrams, right? Let's first start with we'll do a position diagram to just show how the wind is going to be affecting the plane. So let's say we have north, we have southeast, west, right? This is our compass that is typically used when you're talking about plane directions. All right, and we'll draw, let me get this out here, show tabs and commands. Okay, and we'll draw our heading, which is our airspeed first, okay? And we'll just kind of show this coming up here to the origin. Doesn't matter too much how we do this, or where you put this, but this is good enough. So this is, of course, 400, right, kilometers per hour. So we're driving north, right? We're flying the plane north at 400 kilometers an hour. Now, all of a sudden, what happens is a 100 kilometer an hour wind hits us from the northeast. Now, here's the key, right? This language from the northeast is very important. What this is saying is that the wind is actually blowing southwest because it's coming from the northeast. All right, so that's a big distinction. Really what this means is that we have a force affecting us in this direction. All right, this is 100 kilometers per hour. So our plane is being hit by this wind from the northeast. Right? And of course, we have 45 degrees in here, right? Showing that it's from the northeast. Okay, so this is a quick picture of what's happening. Let's now draw a vector diagram, right? Like we did yesterday or in the last lesson, to show how we can basically resolve what happens. Okay, and so the first thing to do, well, let's draw our 400 kilometer an hour velocity, right? And we'll put the wind in beside it. So let's start here, and we'll put a nice big 400 right here. This is the direction that we're starting with, and this is 400. Then, of course, what happens is because the wind is changing our direction, right? What we need to do here is put the wind in such a way that the net effect of the forces will be combined, right? So these two forces act together to give us a resultant, to give us a new ground speed, right? And so in order to show two forces acting together, we have to put them head to tail. We have to add them, right? We add them together. So let's draw our wind from the head of our airspeed of 400 kilometers an hour. And this is 100. Okay, and this means that our resultant, right, is going to be, well, it's going to be from the tail of our airspeed to the head, okay, of the wind speed. And so this here is going to be R. So let's define R, since we just used it. So we'll say let R, okay, represent the new ground speed. And we're also going to use an angle, so we might as well talk about this, and theta as pictured. And what I want to do is just kind of put an angle, put theta right down in there, which I'll explain in a moment. Okay, so if we need to figure out this ground speed, that's vector r, then we need to know, first of all, how long is it, how fast are we going, and in what direction are we going. So since this is north, right, due north, this first airspeed, what we could do is figure out theta, because this would help us to state this as a compass bearing, right, a quadrant bearing. And so if we can figure out that angle and this length, then we should be good to go. Okay, so think for a moment. How could we get more information in this little vector diagram, right? Notice how over here we know a little bit more about the wind speed. We know that it's 100, and we also know that it's coming in at an angle of 45 degrees. So think about how you can move that into the vector diagram. So hopefully you had a chance to think about that. Now, we know that this angle, right, the angle of the airspeed is 45 degrees relative from north, right, from north. And so that's kind of like if we were to draw, right, a vertical line here parallel to a red vector, right, these guys would be parallel, then we would know that this little angle in here is 45. But of course, that would mean that the angle up here would also be 45, right? This would be 45. And hence, so would this angle. These are all 45-degree angles in here. So that's how we can move the 45 over. And really, now at this point, we can find R with cosine law because we have an angle contained by two known sides. So let's set that up. So we know that the magnitude of vector R squared is going to be equal to 100 squared plus 400 squared minus 2 times 100 times 400 times the cos of 45. And so number crunching, the way that goes, of course, is once all said and done here, we get 336.8. And that's what you should get. Crunch out the numbers yourself and make sure you get the right answer there. Okay, and so that gives us our magnitude of R, which is great. That's the first part. But then we also need to know theta, right? But at least now we have an angle side pair because we just got the length of r. So we can use sine law, right? We can say the sine of theta over 100 is equal to the sine 45 over 336.8. And solving for theta, in this case, yields about 12.1 degrees. Okay, so this is great. So now we have the length of r and we have the angle relative to north. So we can say, therefore, the new ground speed is 336.1 kilometers per hour, north 12.1 degrees west. Because, of course, we're pointing to the west. Okay, so part B says, how should the pilot adjust his course in order to maintain his previous ground speed? Well, let's just take a moment now to think about what this is asking, right? So in the last question, right, and I forgot to mention this, but we were asked to find a ground speed, right? This is finding a resultant, right? We were finding a resultant. Where do we end up because of the wind, right? So that's problem A, right? Finding a resultant. Where do we end up? Where are we going? Now this next question is saying, how should we adjust our course to keep our old ground speed? In other words, we don't want to be affected by this wind, so we want to keep going in the direction that we're going. And this is something that pilots have to do, right? They have to account for the wind and figure out how to fly in a direction that they want to go in spite of what the wind is. Okay, so what this means is that we want this previously red arrow, right, to be our green resultant, right? We want a resultant that is 400 kilometers due north, okay? So that's what I recommend starting with, right? We're going to actually just draw our a resultant right away, like this. So here's our 400 kilometers. We know this is 400, and we're going to be going due north. And in this case, I'm just going to draw, I'm not going to draw the position diagram. I'm just going to draw the vector diagram to show how, just basically skip that and to show what we need to do. So we know that the wind is going to be pushing us, right? Essentially, it's going to be pushing on us from this direction, right? From a diagonal 45-degree angle. Right? And there's nothing we can do about that. So what we need to do is just literally attach that to the head up here of our vector. Right? This is 100. So why do we do that? So the reason is because we're trying to now figure out how we should compensate, right, for this wind. So we're going to have to point our plane a little bit into the wind. So it should make sense that we're going to be drawing a vector kind of in this direction, right, in order to account for the wind, right, so that its push isn't as strong. Or another way of saying this is that we want to travel with such a velocity that when added together with the wind, right, so from here to here and added with the wind, we end up where we want to go, right, with this resultant, right? So you want to make sure that that these two vectors, the new trajectory plus the wind, is equal to the resultant that we want. Okay? So now we don't know, right? We actually don't know what the length of this or the direction of this. And so let's actually just add a vector here. We'll call this vector C for change. And we'll say let vector C represent the required course change. It's good language to use. And theta as pictured. So we're going to use, again, we're going to use theta to calculate our angle. Let's of course put it in here up against our against due north, because that's going to help us describe the angle that we want using a quadrant bearing, just the same. Okay, so what do we know about this diagram, right? What information do we know? Well, again, we know that this wind, right, is 45 degrees from the northeast. So we know that this is 45, right? But we also know, notice we also know that this is actually 90 degrees here, right? So because we know these two things, what this means is that this whole angle, right, in the middle, this is equal to 135 degrees. And, right, so now we again have, right, we have two sides with an angle in between, and we're into cosine law again. So we can use that. Magnitude of c squared is equal to, well, it's going to be, again, 100 squared plus 400 squared minus 2 times 100 times 400 times the cos of 135. And after we number crunch, we'll get the magnitude of c is approximately 476 kilometers an hour. And that should make sense, right? This should be longer than 400 and longer than both sides. Not necessarily the sum of both sides, but it should be at least longer than each side. Okay, so there's our speed. Now we just need to know the direction. And that means calculating this angle in here, right? So now that we have an angle side pair, we can use sine law. So sine of theta over 100 is equal to sine of 135 over 476. And after we calculate that, we get approximately 8.5 degrees. So there we go. Therefore, okay, the required course is, so it's going to be 476 kilometers per hour. Now this is the airspeed, right? So I could even say airspeed. The required airspeed is 476 kilometers per hour, north 8.5 degrees east. Kind of like that better. So let's just actually use the right terminology. The required airspeed. Okay. Okay, let's look at example 2. So, example 2 says a river is 2 kilometers wide and flows at 6 kilometers an hour. Anna is driving a motorboat, which has a water speed of 20 kilometers an hour, and she heads out from one bank in a direction perpendicular to the current. A marina lies directly across the river from the starting point on the opposite bank. Okay. So the idea here is that she's trying to actually drive to the marina, and she's pointing her boat initially right at the marina, but the current is going to be moving her downstream. Right? So the first question says, how far downstream from the marina will the current push the boat? Right? Well, let's draw this out. Okay, so we have this river, We'll just kind of orient it north-south, and we'll say that our current is flowing south. Now let's create some points here. We weren't given any points, so we'll say that right here, we'll make this point A, and put the marina right across the river, because that's what the question said, right? It said she heads out in a direction to the marina, which lies directly across the river. And what's going to happen, though, is she's going to end up downstream, right, somewhere down here. So we'll just call that point C. Okay. So what else do we know? Well, we know that the river is 2 kilometers wide, right? So let's do this. We'll actually connect that with a line like this, right? And we'll say this is 2. Okay. Now, what we were told is, right, that we're going to end up downstream somewhere, and so our actual resultant, right, or kind of like our ground speed, or our displacement, really, is going to be something like this, right? And that is due to the water, which is pushing us down, right, downstream. Okay, so the thing that's a little trickier about this one is that, well, as opposed to just working with velocities, right, like we did up here with these airplane questions, we actually have some distances to take into account, right? And so the initial setup, what you should be doing is literally just drawing things and putting in any distances that are relevant, right? And next we can start to think about velocities involved. So these are different than distances, right? Of course, these are direct speeds and directions. So the first thing we know is that the water is going to flow at 6 kilometers an hour and that she can go at 20 kilometers an hour, right? And so what this means is that we can actually put these together, 6 kilometers an hour plus 20 kilometers an hour, and we can create something called a velocity triangle that will be similar to this distance triangle, to this displacement triangle, right? So let me just show you this. So if we put in a vector to represent the water, we'll say it's right here. Okay, and we know that this is going to be 6 kilometers an hour. See, this is the current of the water, so 6 kilometers per hour. And I'll just write that in there to be clear. But we also know that she goes 20 kilometers an hour, and she's literally pointing from point A to B, right? She's pointing her boat this way. And so let's just make a subvector along here, and we'll write, this is not to scale obviously, but this should be 20 kilometers per hour. So this is the velocity that she's going. And so her resultant velocity would be this little green vector from A to here, okay, where we have a right angle right in the corner of these two triangles. So Anna's resultant velocity is going to be the sum of what she is doing, the way she's going, 20 kilometers an hour plus 6. It's going to be this here. And so we'll write this as r, okay, vector r. And so we'll say let r represent Anna's resultant velocity. Or you could even say ground speed, right? Relative to the ground. Where is she headed? Okay, so part A says how far downstream from the marina will the current push the boat? All right, so we actually what we're being asked is how far is this distance from B to C? So in other words, line segment BC is equal to what? So think about this for a minute. Think about how can we calculate BC given what we already have. We know this is right angle as well in the triangle, the two triangles that we have here. Pause the video and see if you can get it. So what we really have here is two similar triangles, right? We have ABC, and then we have this velocity triangle that we made using our velocity vectors. And since we know two sides of the velocity triangle, that means that we could get the other side, this side, BC, relative to AB. So let's set up a ratio. We'll say BC, all right, so this side divided by this side, which is 2, is going to be equal to, in this case, 6 divided by 20. So 6 over 20. Okay, and so doubling everything, of course, BC is going to be 6 over 10, which is 3 over 5 when all said and done. And this is approximately 0.6 kilometers. So what we know is that this distance from B to C is 0.6 kilometers. So we can say, therefore, Anna will end up, we can even say 600 meters downstream. Okay, so part B says, how long will it take for the boat to cross the river? And we know that Anna will be going from point A to C, right? So she's going to be traversing this whole length, and her velocity is going to be r, right? So for this type of problem, what I like to do is, of course, use the good old distance, speed, and time triangle that you probably have seen by now. Distance, speed, time. And because we've been asked how long will it take, we're being asked for the time, right? That will be in right, this part right here. And so if you put your finger over t, what you're going to see is distance over speed, right? So time is distance over speed. So what this means is we need to know how far is she going and how fast is she going, because that fraction, the distance over the speed, will be equal to the time. Okay, so in other words, how far is she going? Well, that means how long is AC, right? We need to know how long AC is. Well, how can we find that? Well, of course, we have AB and BC, right? So this is just simple old Pythagorean theorem, right? So AC is the hypotenuse, so it's going to be the square root of 2 squared plus 0.6 squared. And when that's crunched out, you should get approximately 2.09 kilometers. Okay, the second thing we need to know is how fast is she going? Well, of course, that's the magnitude of r. All right, it's the magnitude of r. And again, we have some sizes here. We have 20 and we have 6, so we could just say that the magnitude of r is the square root of 6 squared plus 20 squared, which is equal to approximately 20.9. And of course, because we have similar triangles, we could have also just used more ratios there, right? We could have found that by just creating a ratio, just like we did up here. So, or we could have even used, we could use tan, right, to calculate the angle, and then use SOHCAHTOA to find the distance of r, the length of r. So we know that this is kilometers and this is kilometers per hour, right? So because these are both in the same unit of kilometers, we can therefore plug these into our time, to our distance time, speed time formula. So the time is going to be equal to the distance, which is 2.09, over the speed, which is 20.9. And when we divide that, we get 0.1. Right, which is equal to, is going to be 0.1 hours, right? 1/10 of an hour, or 6 minutes. Oops, let's change that. Or 6 minutes. And so let's just state that. So we'll say, therefore, the trip takes 6 minutes. Okay, so part C says, is it possible for Anna to travel directly across the river to the marina? If so, what direction should she head, and what's the resultant velocity of the boat? So this one's saying, could she angle her boat upstream a bit, right, in order to counteract the effects of the current? She wants to go straight across. In other words, we want a resultant that goes directly from A to B, right? So the velocity should be along that line. So let's redraw this river for part C. All right, so here's our river. And now we want to have this resultant velocity that goes across like this. Okay, that's her path. But we have this current that we know is going to be pushing us, but we want it to be doing nothing, right, to bring us along to a point along that line. And she's going to angle her boat upstream such that her velocity is along this path, right? So this would then therefore be a right angle, because we know that the current is perpendicular to the direction she travels, right? And what else do we know? Well, we know that she's driving at 20 kilometers an hour, and the current is 6, right? So think about this for a moment. What could we do to determine the length of this velocity, right? This resultant, we'll call this our new resultant, r, and the angle. So hopefully you came up with it. Really, this is just a SOHCAHTOA question, right? We could put an angle in there, and we could calculate theta just using sine, right? We could just say sine theta equals 6 over 20. And so theta equals approximately 17.9 0.5 degrees. And so she has to angle her boat upstream at an angle of 17.5 degrees relative to her path of movement, right, which is horizontal. Or relative to the riverbank, well, we could just subtract that from 90, right? And we could say, like 72.5, right, from the riverbank. However you describe it is fine as long as it's relative to something. Okay, and we also have to know what's her velocity. So we have to know how long that is, right? You could use Pythagorean theorem here again, because we have a right triangle, or we could just use another SOHCAHTOA calculation, right? Because we know that theta is 17.5, and the adjacent is going to be the magnitude of r. That's this length here over 20. And so therefore, the magnitude of r is going to be about 19.1 kilometers an hour. And that should make sense, because now she's taken her 20 kilometers an hour and she's pointing her boat upstream, working against the current, right? The current's bringing her back, cutting her speed down a little bit, right? She's going this way. And so, of course, it's going to be less than the hypotenuse of this right triangle. So that should make some intuitive sense. So let's go ahead and just conclude the problem here. And we'll say, therefore, Anna can travel across the river at 19.1 kilometers an hour if she points her boat 17.5 degrees upstream. Okay, so we've answered C, and let's just finish this lesson here by discussing D. So D says, could Anna make it straight across the river if she were rowing at 7 kilometers an hour? How about at 5 kilometers an hour? Well, notice how we were given, right? We were given 7 kilometers an hour and then 5, right? This first one is actually a little bit faster than the current, which is flowing at 6 kilometers an hour. Well, let's think about 7 for a moment. Right, think about this triangle. How would this change if instead of going 20, right, she was only going 7, right? This would be much shorter, right, this red line. And of course, the angle would be much larger, right? It would be something like this, right? That would look like that. So she'd really have to be pointing her boat upstream to make it, right, using, a 7 kilometers an hour rowing speed. And her velocity, her resultant velocity would be much smaller, right? It would just be this small line here. But she could still do it, albeit a little slower. Now, what about if she was going 5 kilometers an hour? Now she's actually not going faster than the current, right? And so we would have to be trying to draw a hypotenuse along here, right? That was length 5, even though we have a side length here that is 6. Right? So this is actually longer. This would be longer than the hypotenuse. And of course, that's impossible because we can't draw a triangle that has a hypotenuse that's longer than either of the other two sides. Right? So it should kind of make sense as well that if she can't go faster than the current, then there's no way she could completely counteract the effects of the current. And you're going to see that in the assignment as Indiana Jones drifts downstream and heads downstream. You're going to have to think about that, whether or not it's possible. So in other words, she could make it across if she were rowing at 7, but 5 would be impossible. Okay, so that concludes the lesson for today. There's a couple more questions. Well, there's tons of questions down here, right, on page 367. There's also a couple tougher questions right here, just on the last page that you can attempt with the answers given, or at least this answer is given, and I have a solution for this question at least. So feel free to work through those problems, and if you have any questions, bring them to class next day. Okay, thanks guys. Take it easy.